All right, how's it going, everybody? We are here at the beginning of week 14. Um, we are getting ready to wrap this stuff up right here. We are right in the middle of chapter 11, is where we left off, and we are going to essentially wrap up chapter 11 to finish up this class. We still want to hit sections 11.4 through 11.10. That'll happen this week and next week. The good news is that a bunch of these sections are pretty short, including one summary strategy section. So I do think this is going to be perfectly reasonable for us to get through here. So basically what we're going to see here is we're going to hit these guys here today. We're going to hit these guys here tomorrow. Out in week 15 next. And really week 15 is sort of the most, I don't want to say that the sequence series convergence divergence isn't practical, but the most heavy use of sequences and series in the applied math world is probably based on using power series to represent functions. So this is our super important topic that we're concluding with here. So we're going to be hitting these two sections on Monday of next week, and the very, very important topic of Taylor series on Tuesday of next week. It is important enough that I do think that I'm going to give you guys, I don't want to call this like a project because that sounds scary, but I think that a big part of how I'm going to sort of like test you guys over this chapter 11 material is going to be associated with a sort of an explorative activity associated with Taylor series here. And that will, in a sense, be sort of like a piece of your final exam. So that homework associated with the Taylor series stuff will be some like written stuff that you'll submit with your final exam that's out there. Super important stuff, and you will definitely see it come up next semester in Calc 3 and differential equations. And then that just brings us to final exam week. That's week 16, right? So we still got two more regular weeks of content, followed by final exam week here. So again, we're going to hit two sections today, two sections tomorrow. All of them are relatively short right here. I think this 11.6 is the longest, but 11.7 is sort of just like our strategies for integration. It's really just a stop and summarize what we've seen because it's kind of hard to combine all that stuff together kind of section. So just a strategizing section there to kind of clean up all of our convergence, divergence things here. And then our power series is saying, hey, listen, sometimes it's hard for me to think about trig functions and exponential functions and logarithmic functions. Could we come up with polynomial functions that mimic those functions? And the answer is in most cases, yes. So we want to see how can we build representative polynomials to do the job of non-polynomials. That's what we're going to see out there in week 15. Incredibly practical thing to do here. This is, man, used absolutely to death in the applied math world using Taylor series representations of functions instead of the true function itself. So this is not just some extra topic we're squeezing in here. This is, if you're going to see content from this class years from now, there's a huge chance that that's what it's going to be right there is our Taylor series discussion, which is why I'm going to have sort of like our little like mini project that's associated with that I'll assign up there. And again, I don't want to be scary by saying it's going to be a project. It's just an explorative activity there associated with Taylor series here that'll be pretty satisfying, I think, for you guys. The result of it is very, very cool. So that's where we're at. 2 weeks of content in the final exam. So let's get moving here. So the good news for us is that starting today with section 11.4, this title of the section is the comparison test, but we've already seen more than one comparison test happen in this class where we have said, listen, we can't really say for sure what's happening just by analyzing this one series or this one integral, but I can make a comparison between this series or integral to one that I do know a bunch about, and therefore I can deduce the information that I want to know about the complicated integral or series based on what I already know about the simpler integral or series right here. And I keep on saying integral just because the very first one of these that we saw back in the end of like chapter 8 was an integral comparison. We're obviously talking still about series here, about sums, and so we're only talking series here. I was just trying to verbalize that appropriately with what we saw back there in week 8. So again, the good news is we've already done these types of comparisons, so I'm going to assume that you have all been responsible and already read our section here in the textbook on the comparison test. So what I want to do is just look at a couple simple uses of the comparison test. And before I do that, I kind of want to say the general theme of the sections that we are now working through, 11.4, 11.5, 11.6, 11.7. All these sections are really short because they're all basically just saying, hey, here's a theorem you can use to make a decision about convergence or divergence. And that's all that's happening, section after section after section. Theorems on does something converge or diverge. And all you've got to do is just apply the theorem. The issue is that a lot of these theorems are comparison-related theorems, meaning you need to be the person that comes up with a series to compare against. So there is always a little bit of an art associated with determining convergence and divergence of a series because it is up to the prover to imagine on their own what series they would like to compare it against. So this is where if you don't get the content that happened in 11.1 and 11.2, then you're going to be struggling, right? What we have to know about is we have to be very confident in determining the convergence divergence of our P series and of our geometric series. Those are our easiest ones for us to make our judgment call about. So those are the ones that we're going to want to use as our basis for comparisons, right? Whenever we're making our comparison, you've got to start with something where you for sure know about the convergence divergence of that series so that you can compare it to the one that you don't know to end up drawing your conclusion. So let's look at some examples here. And again, I'm assuming if you haven't read the comparison test in your textbook, you should stop and go do that now. I'm going to go ahead and do some comparison tests here. So first one here, the sum of the natural log of n divided by n. So what I'm seeing here, and by the way, I'm going to use our shorthand all day today of sum meaning the sum from n equals 1 to infinity in all cases here today. So I'm just using my Microsoft Word shorthand so I didn't have to spend 30 extra minutes typing to get this ready. So for this infinite series here, what we're saying is we'd like to know if this converges or diverges. And as of right now, we've only got the comparison test as our tool to use. So for these couple examples right here, we're going to only attempt to use the comparison test to see if we can deduce its convergence or divergence. If we get stuck, we'll use a different test in a minute here. All right. So this first sum, the natural log of n over n, I'm thinking to myself, I don't directly know anything about the ratio of natural log to n, right? What I am thinking to myself here is that this does seem related to, say that, related to the series just 1 over n, the harmonic series. What do we know about this? We know this diverges, and why? So, and by the way, this is really important. I'm obviously going to ask you guys some open math questions this week, but all of them are basically going to be like, does it diverge or converge? And you could probably just go through there and click on one, then click on the other, and you're going to end up with all the right answers by guess and check in like 5 minutes. Unfortunately, if you just do that, you're probably going to get crushed by me on the final exam questions associated with these. So it matters that you can prove the convergence or divergence, not guess and check a true-false question. All right. So right away here, I need for you to be able to explain to me why does the harmonic series diverge. I know that this diverges because this is a P series with P equals 1. That's my full justification for this. When we studied the P series in section 11.2, what we judged is that any P series, anything of the form 1 over n to the P as our summation term inside the sum, is going to converge if P is strictly greater than 1 and will diverge if P is less than or equal to 1. This is our edge divergence case right here. A P series with P equal to 1 means it diverges right there. All right, so what I know is that the two things that I'm comparing, the thing I want to know about and the thing I do know about, I know that this guy diverges right here. The comparison that we now get to make is what's the relationship between these two? Natural log of n over n versus 1 over n. And what I know is that when we plug in values of n, okay, all right, so if we plug in 1 for n, we get 0 here, so this term is smaller. If I plug in 2 for n, I'm going to get like a 0.8 or something, so this is still smaller. But as soon as I plug in 3, because 3 is bigger than e, right, that's our 2.718, that's our line that we're crossing right over there. As soon as I start plugging in numbers for n that are bigger than e, which is really just 3 and above, all of these terms are going to be bigger than all of these terms, right? So here's what I know. This series, the harmonic series, diverges off to positive infinity. What I also know is that our series of interest has terms of the form natural log of n over n. Therefore, all of the terms in this series are all bigger than the terms in this series except for the first two terms. So therefore, since this series diverged to infinity, and all of the terms in this series were bigger than the ones in this series must also diverge off to positive infinity. So I'll say here, since the sum of 1 over n diverges and natural log of n over n is bigger than 1 over n for all n greater than or equal to 3, the comparison test, which I will abbreviate as CT, comparison test, is going to say that the sum of the natural log of n over n also diverges. We are bigger than something that diverged off to infinity, so therefore we must also diverge off to infinity. Last thing to kind of notice real quick here, when I make my less than greater than comparison, I'm not making a less than greater than comparison of the sums. I'm making a term by term comparison. I'm saying, hey, if you were to go check out the 47th term, what's the relationship? And what I can see here is that for all terms, for all the infinite number of terms at the third one and beyond, all of the ln n over n terms are bigger than the 1 over n term at its corresponding location in the series, right? 47th term for one is bigger than the 47th term for the other. The 48th term for one is bigger than the 48th term for the other. If that's always going to be true, then our sum has to overall be larger. And since we're larger than something that went to infinity, we will also tend off to infinity out there. So let's look at our next one here. 1 over the sum of n plus ln n. All right? So I'm seeing some similar flavor here in the sense that I see a single n term. I'm seeing a single natural log term. This still seems to me like this is related to the sum 1 over n harmonic, which again diverges because it's a p series with p equal to 1. Right? So I know about the series that I think I should be comparing this to. But what's up with our comparison? What I want to know is the relationship in size between each individual pairwise terms, right? Each individual term of the series in question versus each individual term of the comparison series, which in our case is the harmonic series. What I can see here is that for all n values, I don't care what n is, as long as it's a positive integer, which is the only thing we're considering in all of our series out here, these guys are all going to have larger denominators, and therefore these are all smaller. Right? Right? Remember that upside down A is for all, right? So for all positive integers that n takes on, we're going to see that all of our terms in our series of interest are all smaller than the terms in the harmonic series, which diverged. What our issue here, though, is that if this series diverges off to infinity, and the value of this series is going to be less than it, what we don't know is it less enough that we now converge to something? Or is it just a lesser version of infinity in a sense, right? Infinity minus 10. Well, it's okay, those two are straight up equal to each other, right? Well, we can't say they're equal because they're not numbers. But again, the point here is this is our direction in which the comparison test fails us here. So my comparison test gives us no information. Since our series, the sum of 1 over n plus ln n, is less than our comparison series. Which diverged, right? So what we can't really say is if we have a comparison series that diverges, our series in question is less than that, it's not clear if it's less enough to cause it to converge or if it still diverges, right? So this is one of the places where the comparison test fails us. It doesn't give us any information. As far as I'm concerned, it's still possible that this either converges or diverges. I know that all these terms are smaller than each of the terms in the harmonic series, but I don't know if we've changed by enough to make this thing actually converge out there. So the comparison test here gave us no information because our series was less than something that diverged. That's not going to really make a meaningful comparison for us. Let's go ahead and look at the next example then. 1 over 2 to the n plus root n. All right, so again, I'm looking at this and I'm saying to myself, okay, I don't know about series that have a sum of two different terms in the denominator, especially an exponential term plus a root term. But I can think about some series that I think this is related to, that I do know stuff about. One thing I might think to myself is that this is related to the sum of 1 over 2 to the n, right? That's one that we know about. Does this converge or diverge? Well, I could maybe rewrite this a little bit better as 1 over 2 to the n. So this converges. Why does it converge? It's a geometric series with the absolute value of r being less than 1, right? Here our r is equal to 1/2, right? We have a multiplier every term, a common ratio of 1/2. Since our common ratio is less than 1, this guy will converge. That's what our geometric series test said to us back there in 11.2. So I know that this guy converges. This one seems to be related to it. So let's go ahead and make our comparison. And again, it matters that you can justify this. You can't go ahead and start making a comparison if you can't prove to me what you already know about your comparison series right here. So while these are pretty simple ones, and you are likely going to remake these same arguments over and over again, because I think 1 over n and 1 over, r to the n are like the most common things to compare against out there. It matters that you know why these converge or diverge like they do. Otherwise, your comparison isn't meaningful. Right? Now that I know that this guy converges, we can think about what our comparison looks like for each of the individual terms in the series. Well, 1 over 2 to the n plus root n, those are all going to have a larger denominator than all the denominators in the related series, just 1 over 2 to the n, right? And this is true for all n greater than or equal to 0 right there, because I don't care what you plug. Okay, I should say. If I'm being totally accurate here, it's just greater than 0, but that's okay because we start at 1 anyway, so that doesn't matter to me. All right, so what I'm seeing here is because the denominators of each of the terms here are larger than each of the denominator terms here, these overall terms right here are going to be smaller than these overall terms right here. So anywhere that I go in these two comparison series right here, it's always going to be the case that we're adding up even less stuff in the 1 over 2 to the n plus root n series than we were adding up here. And we know that this guy converged. This series converged to 1. This series is adding up terms that are all smaller than the terms in this series. So I know that this also converges. And in fact, I even know that it converges to something less than 1. But that's not what we get from the comparison test. The comparison test just tells us convergence or divergence. So what does the comparison test tell us? Since the sum of 1 over 2 to the n converges, and 1 over 2 to the n plus root n is less than 1 over 2 to the n for all n greater than 0. The comparison test says that the sum of 1 over 2 to the n plus root n also converges. We know that we added up an infinite number of terms and they still added up to a finite value. When we added up an infinite number of terms that all of them were individually smaller than their related partner term in the other series, then the total sum of that series must be also smaller than the convergent series sum that we got before. So if it's smaller than something that converges and all the terms are positive, it must also converge. Let's take a look at our last one here. We've got the sum of root n over 2 to the n. Again, this immediately, I see that 2 to the n on the bottom, and I'm like, hell yeah, I know stuff about the sum of 1 over 2 to the n. I'll just say convergent geometric. R equals 1/2. This right here is probably the shortest explanation I am willing to receive from you as to your justification. This is a very simple thing right here. It's convergent. It's a geometric series. You can tell me what values we need to have for the geometric series for this to be true. In any geometric series, we need our constant multiplier to be an absolute value less than 1, and we have a constant multiplier of 1/2, so we're in there. So what's our comparison look like here? Well, root n over 2 to the n looks like it's going to be bigger than 1 over 2 to the n for all n greater than or equal to 1. But for all greater than or equal, okay. For all n greater than 1, I guess I'm a little bit off right there in the sense that if you plug in n equals 1, they're equal to each other. I want them to be strictly less than or greater than one another to make this comparison. So here's what we're saying. I know that this series converges to 1. I know that each of the individual terms in our series of interest are all bigger than the terms in the series that converged. I don't know if we just got bigger by some finite amount. So instead of converging to 1, we converged to like 19. Or if we got bigger enough that we diverge. It's unclear to me. Right? So what we always need to do in the comparison test is have a result that's more extreme in the direction of extremeness as the series we're comparing to. If the series we're comparing to converges, we need something less than it to also to claim that it also converges. If we see the series we're comparing to diverges, then we need to be even larger than the divergent series, our series in question, to know that it's also going to diverge out there. So the comparison test gives us here no info here because we are larger than something that converges. Now, I want to say one quick thing before I move away from this right here. In the two scenarios, so in the problems that we just looked at 4 problems right here, we found the first one, we were able to determine its convergence, divergence, and it diverged. The second one, we came up with no information. The third one, we compared to a convergent series and determined that ours also converged. And in the fourth one, we compared to a convergent series but found that we had no information right there. In the two scenarios where we decided there was no information, it's possible that maybe we just need to compare against a different series. I only tried the one easiest thing I could think to try in each of these two cases right here. Maybe it's the case that you can come up with a different series to compare against that does allow you to draw the conclusion. So one thing I want to say to you about this right now is, in a sense, I'm stopping a bit early on each of these two no info cases right here. If you end up in a no information case for the one series you attempted to compare against, you should recognize that there are an infinite number of different series out there, and maybe if you're crafty, you can come up with a different comparison to make that gives you more information than the ones that we just made right here. All right. So I am in a sense stopping a little short right here. It's true, like in this case right here, that I can't go any further with the comparison to 1 over n. But maybe we compare this to like 1 over natural log of n. Well, I don't know anything about that, so I couldn't do that. But maybe like over, okay, right. So like we run into some issues there with that. But again, in these cases, just recognize there's lots of different comparisons maybe that you can make. You just need to compare against a series that you know something about, and there might be multiple choices there. So it's not always the case that you just try one comparison and say, well, we can't do it by the comparison test. There might be other comparisons you should try out there. I'm gonna look at some other possibilities though instead coming up here. So even when the direct comparison test, which is my sort of abbreviator, my longer form version of just the comparison test fails, we can still often manage to use what is referred to as the limit comparison test to help us determine convergence or divergence. So again, I'm going to assume that you've already read this in the textbook right here. Let's talk about what this says, and let's go ahead and use this to revisit our examples that didn't work out a minute ago. What the limit comparison test is going to say is, again, is a comparison of two different series. We can see them right here. My one series defined by the a sub n terms, my one series defined by the b sub n terms. The limit comparison test is going to say, listen, if you take the limit as n goes to infinity of each of the terms of these series, and if that limit exists, and if the limit converges to some value, some positive value c, then either both of these series converge or both of these series diverge. So here's really going to be the strategy associated with this. We're going to take a series, we'll call it a sub n, that we don't know about the convergence or divergence of. We are going to choose ourselves a series b sub n to compare it to. We're going to take the ratio of each individual term, a sub n and b sub n right here. And if the limit of the ratio of these terms converges, then we will know that either both of these converge, and that's useful to us because we chose a comparison series that we know about the convergence or divergence of, or they're both going to diverge. All right, and so since we allegedly picked something we know something about, that will inform us about the thing that we don't know something about. The book walks through a proof of this, and the proof is good, but the proof and the proof like makes sense to me. I read the proof and I'm like, it makes perfect logical sense. You should read the proof in the book; it will make logical sense to you as well. But that proof doesn't like follow my intuition as to why this is true. So I just want to talk about this real quick here. I like to think about sort of the opposite case here. What if this series and this series didn't have the same behavior? What if one converged and one diverged, right? If a sub n converged to some constant, but b sub n diverged off to infinity, then when we take this limit, what we're going to see is a constant divided by infinity, which is going to take us to 0, which is not a number that's going to satisfy this. The other thing that could happen is if a sub n diverged and b sub n converged, or the series associated with them diverge and converge, then here we'd be getting a constant term, a sub n, divided by maybe a 0 term for b sub n, since it's a convergent series, and that would tend off towards infinity for c, and that wouldn't work. So notice that it needs to be the case that, in a sense, these terms grow at some sort of comparable rate right there, right? And so again, I feel like my intuition for the limit comparison test is to think about sort of the complete opposite scenarios. This start here and start by thinking about what would happen if a sub n and b sub n had opposite convergence. One converged, one diverged. Then I think you could see that you're guaranteed to be getting out either 0 or infinity from this limit in all of those cases. So that's, I feel like, the contrapositive of this theorem. This theorem says if A, then B. I'm saying if not B, then not A. That's the contrapositive. I flip the statement and I negate both parts. If the forward direction is true, then the contrapositive will also be true. And I feel like I am more down with this statement by its contrapositive right here. Assume the opposite of the conclusion, and that will imply the opposite of the hypothesis right there. I feel like that way kind of agrees with my intuition about limits. So here's the thing to remember. Even though this is sort of now reducing us down to a limit computation to help answer our question, don't forget that this is still a comparison test. I mean, it's in the name. It's sitting right there, right? The point is that we're always going to have been given a series that we don't know about, and we always will need to choose a series that we do know about because of that word right there, because they'll have the same behavior ultimately, that we can perform this ratio limit with right here. So what I want to do to kind of use this right here is let's go back to these two that we couldn't answer a minute ago and see if the limit if the limit comparison test helps us. So we failed to decide on this one, and we failed to decide on this one. So let's go revisit each of these down here with the limit comparison test and see if that helps us. Right? This is the first one, right? So the first one we couldn't get information about was the 1 over n plus ln n. So now let's look at this guy here, right? So I'm thinking to myself, I still think that it's appropriate. I still feel like I want to compare to the harmonic, right? That's the parts I see in there, the 1 over n. I see those parts. It looks like that to me, just with extra stuff, right? So what I'm going to do is I'm going to say, let's go ahead and and by the way, our order really doesn't matter for this right here. It doesn't matter which one you pick as a sub n and which one you pick as b sub n. You should notice that if we flip a sub n and b sub n, we would just get 1 over c instead of c. But if c converged to a number like 86, then we're going to get 1 over 86, which is also another positive number. So it really doesn't matter which one you pick as a sub n and which one you pick as b sub n. Should not be relevant. It doesn't matter. It should work out either way the exact same. And so what I'm going to do is I'm going to say, let's let a sub n be the 1 over n plus ln n. And let's let b sub n be our comparison series, the 1 over n. I know that this one diverges. So if we can get the limit of the ratio of the terms of each of these two series to be equal to a constant, then since this one diverges, this one must also diverge. If we get something not equal to a constant, then we still have no information. Okay, let's do it. So we're going to do our limit as n goes to infinity of a sub n over b sub n. That's going to give me 1 over n plus ln of n over 1 over n. By doing a little bit of flipping my bottom fraction up top here, this is going to be, oh, I forgot my limit statement right here. Limit as n goes to infinity of n over n plus ln n. Not super clear to me what's happening there. I think here is a good appropriate place for us to do our smart factoring techniques associated with this guy right here. So I'm going to factor out n from the top and from the bottom and cancel them. And what I know is that natural log of n is always going to be smaller than n for n being bigger than 1. So this little guy right here is going to go to 0, telling me that this limit is equal to 1. Since this limit is equal to 1, which is like a constant c that is positive, then it must be the case that both of these series converge or both of them diverge. Since the harmonic series diverged, we are then guaranteed by the limit comparison test that this series also diverges. By the limit comparison test, sum of 1 over n plus ln n also diverges. And again, technically here, one of the things I slightly glossed over, I should say, or I'll just put this right here, we do need to give our light little justification that this thing diverges. P series of P equals 1, so it diverges. Right? So since this is known to diverge, and these must have the same convergence or divergence, our series will also diverge right there. So here, the direct comparison test with 1 over n didn't get us there, but the limit comparison test with 1 over n did end up getting us there, which is pretty cool. Let's go ahead and take a look at the other one that we couldn't get our hands on. Here's the one that we couldn't do a moment ago. I still feel like I want to compare with 1 over 2 to the n as a series. I'm going to say here converges geometric series with r equals 1/2. That's my full justification for how I know it converges right there. And so let's go ahead and let a sub n be root n over 2 to the n. Let's let b sub n be just the 1 over 2 to the n. And we can go ahead and investigate limit as n goes to infinity of a sub n over b sub n to be the limit as n goes to infinity of root n over 2 to the n, all divided by 1 over 2 to the n. If we clean up this fraction a little bit, this is really just going to leave us the over 2 to the n's cancel, and that just leaves us with this. All right. So what we found is we did not find that our limit converged to some value. So this is therefore going to give us no info from the limit comparison test. Right? The limit comparison test requires that the ratio of the terms have a limit that tends to a constant. Our limit diverged to infinity, so we get no information from the limit comparison test. So you should notice with this one, we're double stuck. The comparison test with 1 over 2 to the n gave us no information, and the limit comparison test with 1 over 2 to the n also gave us no information. Looks like this one is going to require some alternate technique for us that we might be able to work out in the next few sections out here. All right. So out of the 4 ones that we started with, 2 of them were possible with the comparison test and 2 weren't. Then we hit the 2 that couldn't be handled by the comparison test with the limit comparison test. One of them ended up being able to be manageable, and still one of them also provided no information. Remember, we're not getting, these are one-directional theorems right here. It's not saying if it goes to infinity, then they have opposites, convergence or divergence or something like that. We only get the one direction of this statement. If this is true, then this is true. It's not necessarily the case that says if this is false, then this is false. It's not necessarily guaranteed to be true right there. So don't go ahead and just assume the opposite type of convergence. This is just a no information from this test right here. So let's go ahead and look at a couple more examples. I just want to do like 3 more examples right here using the comparison and limit comparison test, and then we'll talk about some alternating series here. So let's go ahead and check a few more series for convergence and divergence here. So what I'm seeing here is this sum, 2 over n squared plus 4. So what I'm thinking of right away is I feel like I want to be thinking about things like 1 over n squared. Right? But I've got 2 over n squared plus 4. So I want to kind of make the appropriate algebraic arguments that this is a reasonable thing to do. So the first thing I think that I want to do here is say, listen, this is just a constant multiplier by 2. The only thing that's trapped inside of our summation is all of the terms that are fully dependent on n, which in this case would be our denominator. But it looks to me like this is just a constant multiple by 2. So one thing I'm saying here is that 2 shouldn't come into my conversation here. If this series converges, then so will this series to twice as much what the value is. Multiplying a number by 2 will never make it go from being finite to infinite, right? If this series converges, then so does this one. If this series diverges, then multiplying it by 2, this one will also still diverge, right? So if whatever I know about the 1 in the numerator series will be equivalent convergence for the 2 in the numerator series that's happening over there. What I feel like I want to do is compare the series 1 over n squared plus 4 to the series 1 over n squared, because this is something that I know about. This is a p series. 1 over n squared converges. Short argument, it's a p series with p equals 2. Remember that a p series converges if p is greater than 1. That's the power that's on the end that's sitting in the denominator right there. The comparison is, what do we have here? Well, 1 over n squared plus 4. Notice that all of these denominators are larger than the denominators associated with 1 over n squared. So all of these terms, every single term that's in this infinite sum is smaller than its comparative term in this known convergence sum. Therefore, we must also converge. So by the comparison test, the sum of 1 over n squared plus 4 converges. So therefore, finally, I think I can say 2 over n squared plus 4 converges, because it will just converge to twice as much. And if this converged to some number c, then this just converged to 2 times c is the only difference right there. All right, so we found this to converge by the comparison test. This next one's pretty cool right here. I like this guy. And I like all these ones that sort of compare things to the harmonic series or something to the nearby harmonic series, right? This one, again, I feel like this looks like 1 over n. But kind of what we decided is that, in a sense, the harmonic series is sort of, and it's not truly the edge, but it feels to us like it's the edge between converging and diverging whenever you have that 1 over n thing here. What I can see here is that all of these denominators are all going to be larger than just the number n. It's 2 times n plus 3. So all the terms in this series are all smaller than the terms of the harmonic series. But are they smaller enough to make it converge? It's not clear to me. So let's go ahead and take a look at this thing with the comparison test right here. What do we see? By the way, the other thing that I want to say here is I want to relate this to this guy. So what I want to do is I want to algebraically make it look as much like that as possible. So what I'm going to then do is I'm going to say, well, I could write this. I could factor out a 1/2 from the bottom. And this now feels a little bit better to me because now I'm more directly getting this 1 over n comparison thing. That coefficient of 2 sitting out there was really just a constant multiple, so I pulled it out in front of my sum. Just like you can pull a constant multiples out in front of integrals, sums dealing with the same kind of idea right there. So let's compare to 1 over n, and we say this diverges. This is a p series. P equals 1. And what do we see here? Well, I see that 1 over n plus 3 halves. All of these terms are smaller than 1 over n because the numerator is bigger, right? But what does that tell us with the comparison test? Well, the 1 over n series diverged. our series is clearly smaller than a divergent series. That's our no information scenario. It's not clear if we're smaller but still infinitely large or smaller enough that we actually converged. So I'm going to say here, no info from the comparison test, from the direct comparison test. So since the direct comparison test failed us right here, gave us no information, let's go ahead and see if the limit comparison test will give us information. In this case, I'm still going to use the same two things. I'm still going to let like a sub n, and in this case, I'll just kind of, it doesn't, whatever, it doesn't really matter. We want to know what's up with this limit, right? So I've been given this as my individual terms. I'm comparing to the individual terms of the harmonic series because I know that the series b sub n diverges. And so our limit a sub n over b sub n is going to be, limit as n goes to infinity, 1 over 2n plus 3, all divided by 1 over n. I do a little bit of my limit math right here, or a little bit of my algebra, honestly, here. This is limit as n goes to infinity of, this will be n over 2n plus 3. And I'm hoping that what you remember from our limit arguments here is if the powers, if both the numerator and denominator themselves are polynomials, then the highest ordered term in each is the decider here. So here, this is really just like n over 2n, and the n's cancel, and we're going to get 1/2. Or you can think about this as factoring out n from each top and bottom and getting 1 over 2 plus 3 over n. And now, as we let n go to infinity, this is 0, and we are going to get 1/2. So notice that the ratio of the terms limited to a positive constant, that is exactly what we are looking to have happen in the limit comparison test. Therefore, both of these series converge or both of them diverge. I know that the 1 over n series diverged, therefore this series also diverges. So it looks like we were smaller than a divergent series, but not smaller enough to make us converge. This is still going to diverge off to infinity out there, just by doing some constant multiples out there. So this says by the limit comparison test, here's 1 over 2n plus 3 also diverges. The also, I think, is kind of important right there because the whole reason we knew this was very much dependent on our knowledge that this series diverged. So again, our knowledge of these base case scenarios for these series is wildly important because it gives us access to infinite more series that we now know about because we can just make comparisons with things that are like core, our geometric and our p-series out there. Since we know that those converge or diverge, anything that we can make a meaningful comparison to, we now know about the convergence and divergence of all those with these two comparison tests that we get right here. Right? So the comparison test says pick something you already know about and compare against it, either by judging if each individual term is greater than or less than within the sequence, or by looking at the ratio of the individual terms and seeing if the ratio is going to be a constant multiple ratio or not. That's the limit comparison test out here. So I'm abbreviating these as CT and LCT for comparison test and limit comparison test. We're about to have a whole bunch of comparison tests here. We're going to get more next week even, and so, or tomorrow. So cool, I really like these. And again, before we move on to our next section right here, remember, it's dependent on you to stop and say, what does this sort of feel like? If I were to just strip parts away and make this something simpler, what would it be? It is often that you are hunting for a harmonic for a p-series, a harmonic is a p-series, or a geometric series, because those are just the only two collective families of series that you for sure know about their convergence or divergence. Right? Oh, we have one more. Ooh, I thought we were done right there. Let's do this last one right here. So our last one here, let's go ahead and try and see what we can do comparing this one. So comparison. So 1 plus sine of n over 4 to the n. I immediately get a little bit weirded out when I see trig terms crop up in these because I know that trig terms are always doing a little bit of wobbling back and forth. They're always doing a little increasing. They're always doing a little decreasing. We're going to need to be careful with trig terms. That's going to be very much true for these last 2 weeks right here. We're going to see this is sort of a special trig term case. Later, we're going to see, today, we're going to see a sort of special trig term case right here as well. So what should I compare this to? Well, I guess the thing that I'm seeing here is just a 1 over 4 to the n, also known as 1/4 to the n, which is a convergent geometric series with r equals 1/4 right there. Any r value between -1 and 1 will cause us to converge right there, according to their geometric series rules that are out there. So let's do a comparison. So what I want to do is compare these two. I'll put my little comparison box right there. That's my greater than or less than. So my question to you is this. Are all of these terms larger than or smaller than all of these terms? You should notice that this one's kind of an issue. You should notice that sine sometimes takes on values like, for example, -5. And in the -5 case right there, we'd only end up with a numerator of 1/2, which would make this a smaller term. On the other hand, sometimes sine spits out values like +0.5. In that case, this would be 1/2, in which case this would be larger. So our issue here is that there's no guaranteed relationship, less than or greater than, for all n. So I can't use this as my comparison series. All right? This comparison just didn't work out. So I don't know what I'm going to do with that guy, right? So this is where I should then maybe say to myself, all right, well let's try the alternating series test then. Or sorry, the limit comparison test, alternating series. 1 second here. In this case, I would say that my a sub n is our 1 plus sine of n over 4 to the n. My b sub n would be my just 1 over 4 to the n. And I am interested in the limit as n goes to infinity of a sub n over b sub n, which is 1 plus, hold on, let me get my limits in there. So just like we saw before, the over 4n's are going to cancel. And now we're left asking the question, what is the limit as n goes to infinity of 1 plus sine of n? What we know is that this is an oscillating expression right here, 1 plus sine n. This never settles down to one value right there. This just keeps on wobbling between 0 and 2 all the time, right? 1 plus sine has just been shifted up by 1. So instead of being between -1 and 1, it's between 0 and 2, and it just oscillates forever. This is dne by oscillating. So there's no info again, right? So no info from this comparison, no info from this limit comparison test. Now here's the thing I'm kind of thinking. Maybe I just picked the wrong thing to compare against, right? Kind of like now I'm stuck, right? This is one of my natural like I'm stuck situations, and it's dependent on us to stop and think of series that we can compare against that we can actually make these calls on, right? What I want to do is it needs to be the case that whatever thing I'm comparing against, so maybe 1 over 4 to the n was a bad choice on my part, I want to be able to make for sure this distinction. Is it greater than or is it less than for all n? If I can't come up with that, can't use a comparison test. Or I need to be in a situation where I can get this limit to converge. What I'm thinking is I don't know how I'm ever going to get a limit to converge if it has this trig term in it, or just a straight up trig term, not like 1 over n sine of n should eventually go off to 0 out there, but like this is just a straight up sine term. Like I don't know how I'm ever going to get this to converge. If I'm ever going to make an answer about this one, I feel like it's got to be from a comparison, but it looks like we picked the wrong thing to compare against. So My new question is this. Can I pick a very closely related function, different, and I shouldn't say function, a series definition, 1 over 4 to the n? That didn't do it for me because I was unable to make this broad statement about less than or greater than. Why? Well, maybe here's the way I go about asking myself this question. My issue here was that our numerators weren't always just bigger or just smaller than one another. Our denominators obviously all match. Is there a numerator I could have picked for my comparison so that I could guaranteed know if it's going to be greater than or less than? And the way that I can answer that is by saying to myself, well, what span of values does 1 plus sine of n take on? I say I need a new comparison. I know that sine of n is stuck between -1 and 1 always. If I add 1 to both sides, then I can see that 1 plus sine of n is always stuck between 0 and 2. I'm trying to come up with something that I know it's bounded by. It seems like maybe if I had just chosen our numerator to be 2, then I could have actually made this claim. All right. I still know this converges. Whatever that thing converges to, it's just converging to 2 times that now. That's okay. Still a finite value right there. Now, if I do my comparison, I'm now looking to judge 1 plus sine of n over 4 to the n. Put my little comparison box right there again, hoping I can actually fill it, over 2 over 4 to the n. What I can see now is that these numerators here are always going to be less than or maybe equal to right there. Although you should realize that if we're thinking of the sine as taking in radian measures here, there's never going to be an integer number of radians that's going to give us sine being exactly 1. It's always going to be some fractional amount of pi right there. So in fact, it's actually the case that we get strictly less than as long as get less than, not just less than or equal to when n is an integer, when n is an element of the integer set right there. All right. So the important thing is just by changing what we compared against a tiny smidge, it didn't change whether or not that thing converged, but it did increase our ability to make the comparison that we want to make. I now know that our series in question has terms that are all smaller than the terms of a convergent series. So now I can actually conclude by just the regular comparison test that this series converges, right? So this is what I'm saying about making our smart convergence choice or smart comparison choice right here. Don't just pick the most basic thing and walk away from it. We want to stop and think about where things live. 1 plus sine of n, where does it live? It lives between 0 and 2. So if I want to know, that helps me bound it. I mean, that helps me say, I know that if we're comparing it to 2, it's always less than that. Important statements that are like that, right? So by the comparison test, the series 1 plus sine of n over 4 to the n also converges. Don't know what it converges to, but I know that since 2 over 4 to the n converges because it's a geometric series with r equals 4, or r equals 1/4, and since all of the terms of our series in question are smaller than all of the terms in a convergent series, then our series must also converge by the comparison test right there. So I like this one because I tried my lame thing at first and got stuck. I tried to stick with my lame thing and use a different strategy and got stuck again. And then I went back and changed my comparison series and I got unstuck right there. And I did that just by stopping and thinking to myself, what would I need to make this denominator so that I could make this statement of less than greater than right there? And we did. So great examples right there. I really like a lot of these. These are fun. And you should see with these, again, all we're trying to do is make a yes or no decision, but kind of prove that our decision is correct here. And as I'm hoping you can see, there's a little bit of an art to this, of like kind of picking the right choice up at the front so that you don't have to try a whole bunch of things in a row right there. So that's our comparison test right here. I want to talk about our alternating series now, and then we'll look at a bunch of examples for these as well. An alternating series is any series that changes sign, positive, negative, positive, negative, positive, negative. Any alternating series, since it's always changing sign, can always be written of the form negative 1 to the n times b sub n. So b sub n is like the term, is like the positive part of the term without any sign consideration. Negative 1 to the n, since n is always going to be integers, is always going to be either negative 1 or positive 1, depending on if it has an even or an odd power. You will see, by the way, that I think the book denotes this as an n plus 1 up there. You should notice that in this case right here, when I have this listed at n, since our sums typically start at n equals 1, that would mean our first term is a negative. If instead I had n plus 1 as my power up here, then with our first value of n being 1, 1 plus 1 would be 2. We'd be taking an even power on negative 1, and our first b sub n term would be positive. That's just up to you to determine, is the first term of the series positive or negative? Determines whether or not you want a n or an n plus 1 up in the numerator attached to that negative 1. So again, this is determining the sign of the term. This is determining the magnitude of the term, the b sub n. All right, so b sub n, we're saying, is always positive. The negative part, the flipping back and forth negative part, is always handled by that negative 1 to the n power. The last thing I want to say before I walk away from this definition is I would like to highlight that word. Not all alternating series are written with a negative 1 to an n power. All of them can be written that way, and that's really important. We're going to see that for our final example here today. This word can will come back to us right here. There's one essential test associated with determining convergence and divergence of alternating series. By the way, I should point out, we're in section 1.5, 11.5 and 11.2, 11.3, and 11.4. Every single test or theorem that we've had has required that we only have positive terms in our series. All of them required only positive numbers to be considered in our sums. This is us now saying, well, I don't know, maybe we add a little, then subtract a little, then add a little, then subtract a little. So the point of this section right here is just to say, maybe there's negatives out there too in your sum. We should be able to deal with that also. This is a special case of where we alternate back and forth between them being negative numbers right here. Not just some mishmash of positives and negatives. It has to alternate back and forth, one then the other. And the good news is that our test associated, the alternating series test for convergence or divergence for an alternating series, is very similar to the same concept of the monotonic sequence theorem. So let's remember this one. The monotonic, and remember, this is about sequences. This is from section 11.1, not a series. The monotonic sequence theorem said, if a series is monotonic and bounded, then the series is convergent. Our example for this, our little like graph said, if it's monotonic, then we could say, for example, it's always increasing, right? If it's always increasing, it's always getting bigger. But if it's bounded above and it's always getting bigger, then it has to converge, right? Because it can't possibly make it off to infinity, and it's not oscillating. And I know it's not oscillating because it's monotonic. Right? We're getting sort of like a bouncing back and forth version of that for the alternating series test. The alternating series test says, given a general alternating series, that's just my general form of an alternating series, and you should notice here, we've just got b sub 1 minus b sub 2. Okay, all right, I'm going to make this technically a little bit more right here. Notice my like little technical error in this one right here. When we start at n equals 1 would say that my first term should actually be negative b1, and I have it written as positive b1. But notice that if I make this like that, then now this is going to say when I plug in n equals 1, then we now have an even power. So negative 1 squared is positive 1, and we do get a positive first term. But then we'll have an odd power for the next one. So we get a negative second term, stuff like that. So b1 minus b2 plus b3 minus b4. And again, where I'm saying that all the individual b sub n's, their magnitudes are positive, I'm handling the sign within the summation out there. Right? So what do we have? Well, if each consecutive term is smaller than the term that came before it, if b sub n plus 1 is smaller than b sub n, and remember, we're not talking about the positive or negative part. That is completely handled for us with a separate term. We're only talking about the magnitudes of the terms in this comparison. So we're saying if the magnitude of a later term is guaranteed to be smaller than the magnitude of the earlier term for all n, and if our terms, if the sequence b sub n, not the series, if the sequence b sub n tends to 0, then we'll be guaranteed that the series is convergent. The book does draw a very nice static picture of this. This is one I feel like there's probably some awesome video out there on the internet that I was unable to find. But they kind of suggest that if our terms are bouncing back and forth relative to 0, if they're always getting slightly closer to 0, then they have nowhere else to go but to add up to some terms that are going to converge onto 0. The book gives a pretty nice graphical explanation of it. But again, when you're thinking about why the alternating series test is true, it's true for, it's sort of like a two-dimensional version of the one-dimensional series thing that's going on here because we can bounce it around to both sides. But the argument for the alternating series test is very, very similar to the argument for the monotonic bounding theorem that's happening right there. The only difference is we get terms going in both directions. So the book argues about the individual partial sums. The partial sums are going to have are going to tend to 0 there. Therefore, the series is going to be convergent. So let's use this alternating series test. So check it out. Anytime we see a series that alternates in sign between positives and negatives, it is an alternating series. We would like it to be able to be written in this form. We want it in this form because our two requirements for the alternating series test require us to talk about just b sub n with the alternating part of it kind of removed, right? That's handled separately by the -1 to some power. So I always want to be able to show that the magnitudes are decreasing. It's a decreasing series, without worrying about the positives and negatives, and that the sequence of terms in our series does converge to 0. If I can do that, I'll know we're convergent. If I can't do that, we get no information. This isn't otherwise it diverges. Right? So let's go ahead and take a look at a bunch of examples here, and we'll do these 5 examples, and we'll go ahead and call it a day. I know I'm going to need more room for each of these here. 3 on a page maybe. All right, so we've got our first alternating series here. It's clearly an alternating series. It is clearly the case that this is our b sub n term right there. That is our magnitude of each term. They're going to bop back and forth, positives and negatives right there, but their magnitudes are captured right here with b sub n. So alternating series test says to me, what I want to be able to show is that each subsequent term is smaller than the previous term. I also want to show that the limit as n goes to infinity of b sub n is equal to 0. In this case, both of these are pretty not exciting right here. We need to show that b sub n plus 1 is less than or equal to b sub n. The way that I think that I can show this is that since the numerator has a since the denominator is a polynomial of higher degree than the numerator, I know that the rate of change of the denominator is greater than the rate of change of the numerator, and it's positive. So I know that every subsequent n that I plug in that's bigger than the one before will increase the disparity between the numerator and denominator, making our fraction smaller and smaller and smaller. So I'm just going to say here, since the denominator grows faster than the numerator, n squared versus n, this is a decreasing sequence. Right. We'll do a little bit more of a formal one on this one. I think that we can all kind of visually see that the denominator will be growing faster than the numerator. And in fact, I might even go so far as to say the numerator growth rate and the denominator growth rate. Right? So for all n greater than or equal to 1, the denominator's growth rate is guaranteed larger than the numerator's growth rate, and so we are going to continue to see this fraction get smaller and smaller and smaller out there. Okay? So I know it's decreasing. For the second part, I need to show that the limit as n goes to infinity of b sub n is equal to 0. This one, hopefully you see, is directly, obviously true right here. I'm going to factor out n squared from both parts right there. And what we can see is we're going to get a 0 over 4 plus 0. We're getting 0 right there. So by the alternating series test, this alternating series is going to converge. All right. So all we got to do is show that the magnitude of the terms decrease over time, and show that the limit goes to 0 of each of the terms. Right? This one wasn't super exciting. This is just a rational function. Let's look at some ones that are a little different, right? So here we're seeing some exponential terms, also with some crappy powers in there. We're seeing some that aren't even given in an appropriate form. And by the way, notice this last one out here doesn't have some -1 to a power term. So we're going to need to figure out some alternate version of that guy right there as well. So what do we got here? All right, so we're looking at our sum of -1 to the n of e to the 1 over n over n. So, all right, let's see here. So I'm kind of, I don't know about showing this thing's decreasing. That seems a little bit weirder. So maybe I'm going to do my step 2 here first, which I think is going to be a little bit nicer. And again, we've got b sub n right here. Right? Here's what I'm seeing happening. It looks to me that as n tends off to infinity, we're getting stuff that looks like e. So we're getting 1 over infinity, which is like 0 up top, over infinity. So that's going to be like a 1 over infinity. That's us going to 0 right there. So it does look like we're getting, the denominator gets infinitely large, but the numerator is approaching 1. And 1 over infinity, we're going to tend off towards 0 right there with that limit statement. Right? So I feel pretty good about that limit. The next part, that's a little bit weirder to show, is showing that we're going to get a decreasing terms in each case. Now, this is different because this isn't a function, right? So that's why like this argument up here is sort of not great, because we're not talking about some functions. We're talking about values of a sequence. It's discrete. It's not a continuous thing right there. 3, I'm going to put a 3 right there. This is step 1. We want to show the sequence b sub n is decreasing. So what I want to show is that b sub n plus 1, so want to show, WTS, that b sub n plus 1 is less than or equal to b sub n. Well, let's just literally work from that inequality right here. I'm hoping to confirm that, what do we got? E 1 over n plus 1 over n plus 1 is less than or equal to e to the 1 over n over n. This is what I want to show is true. I'm not sure if it's true. I want to do a little bit of algebra to get me there. Well, the thing that I'm seeing that makes this uncomfortable for me is it's uncomfortable for me to have a ratio of exponential and polynomial compared to a ratio of exponential and polynomial. So I'm going to do some, I guess, cross multiply here. Gosh, I hate the concept of cross multiplying. I'm moving terms around. I'll multiply both sides by n plus 1 and divide both sides by e to the 1 over n. And here's what I'm seeing. Is this true? Is this true for all positive integer values of n? Well, here's what I know. I know that n plus 1 over n is greater than 1 for all n because it's got a bigger numerator than denominator all the time. That's one thing I know. Here's the other thing that I know. What's going on over here? Well, this is, for example, like e to the 1/6 over e to the 1/5. If I take a sixth root of e, it's going to be smaller than if I only took a fifth root of e. So it looks like this ratio over here is always going to be less than 1. Right, think about an example right there. A sixth root of e, the more roots you take, the more crushed down towards 1 this thing will be. So if you've taken fewer roots, then you are not as crushed down towards n right there. Right? So what I'm seeing here is that this term on the right is always bigger than 1. This term on the left is always smaller than 1. Therefore, this equality is guaranteed to hold. Thus, we can conclude by the alternating series test that the sum of -1 to the n of e to the 1 over n is going to converge. Right? I did show that its limit was equal to 0 of the individual terms. I did show that the magnitude of the terms was decreasing over time. And so it looks like we're guaranteed by the alternating series test that this guy is going to go ahead and converge. These types of algebraic arguments right here, super duper important. If you can't show that the sequence is decreasing, then you can't use the alternating series test. And that means you can't talk about alternating series. So you have to be able to do some of these algebraic manipulations and make some more logic arguments. I mean, I hope that you guys are seeing that this is very much more of a proof than any sort of computation, right? We're only really trying to make a decision, converge or diverge. There's obviously just two choices. But if you can't prove to me that this thing converges using theorems and facts, like we're showing right here, guarantees of inequality relationships, then you can't use these theorems, right? So this is really like, to me, the bulk of the work right here. Being able to compute these limits, being able to prove these inequalities for relationships. This is ultimately saying, prove a sequence decreases. And if I couldn't do this algebra, if I couldn't make these two little sub-arguments, then I couldn't have confirmed that this statement was true. And you've got to be able to make those reasoning, logical arguments. And again, by the way, if you just get to this statement right here and say, and since this is always true, then I'm going to not give you any points because it is very not obvious to me that this expression is true. So don't just go making wild claims without obviously proving that they are true every step along the way. These two lines of work are absolutely 100% required to do this problem. And I don't know any way to conclude that this series converges without showing each of these two individual inequalities right here to justify this inequality, to justify the decreasing nature of this sequence, right? These justifications matter, or you haven't proved anything. You've just suggested something. And I will never say, suggest whether this converges or diverges. I will say prove in every case. And if you haven't proved it, then you didn't do it, all right? So these steps really, really matter here. Let's look at a couple more here. Next two I think will be easier, but we still want to rephrase these in terms of series on our own. So our first guy right here, I'm seeing 1 over 3 plus 2 over 4, 3 over 5, 4 over 6, 5 over 7. I'm seeing very obvious patterning in the numerator and denominator. I'm seeing that these do alternate sign with every new term that we get. We have in the next sign. So this does seem to me like it's appropriately representable as an alternating series. So I think that I can write this as its sum. I want to write this as the sum because I need to be able to discuss b sub n to know if this converges or diverges. I need to know what b sub n is going to be. So it does look like we should have some -1 to some power. I'm noticing that our very first term is actually negative, so I'm just going to give it the power of n because I'm going to start at n equals 1, and so I want an odd power to make this thing negative. What does it look like all these terms are? Well, these are all literally just n. The numerators literally have n in the numerator. First, second, third, fourth, fifth term out there, right? So our numerator is n. What's our denominator? Well, the denominators also linearly grow by 1, but they started at 3. So if n typically starts at 1, then this should be n plus 2, I think, for all these denominators down there, right? So importantly, I have rewritten this explicit series as its summation. I needed to do that so that I could claim what my b sub n is going to be. Now we can attempt to use the alternating series test to determine if this is going to converge or diverge. So what do we know? According to the alternating, again, just come back to this guy. According to the alternating series test, I need to see that the limit as n goes to infinity of b sub n is 0. I need to see that this is a decreasing, that the magnitudes are decreasing. One thing that I can see here is that it doesn't look like our magnitudes of the terms are decreasing. This is 1/3. The next one is 1/2. Or excuse me. So right away, literally just by looking at the first two terms of the sequence, I already know that according to the alternating series test, we're not getting any information about this guy. I already know that because this is not a decreasing series. Right? And the other thing I know is that the limit as n goes to infinity of b sub n, I can see this here. It's the limit as n goes to infinity of n over n plus 2. I can see what this is getting close to right here. It's getting close to 1. So both parts, we failed both of the hypotheses of the alternating series test. And again, that just means it doesn't give us any information. It just means we just can't use that thing right here, right? But we actually know some things about this sequence based on the divergence test out here. Uh, so B sub n is the positive stuff. Right? If we talked about just the series, or the sequence a sub n being exactly what we're looking at here, -1/3, 2/4, -3/5, 4/6, right? What we saw in section 11.2 was that if this series does not converge, or sorry, if this sequence does not converge, then the series does not converge, right? So now you've got to remember back to our previous tests. The divergence test in 11.2 said if the individual terms of a sequence don't converge on some value, then our sequence, or then our, sorry, if the individual terms of a sequence don't converge to some particular value, then the series itself is going to diverge. So, importantly here, we saw that this was an alternating series and we attempted to use the alternating series test. However, our series failed both of the required components to use the alternating series test, so we got no information from it. But what I can see is that what's going to end up happening here, it looks like, is these terms are going to ultimately get really close to basically just being like +1, -1, +1, -1. Like that's what this is almost going to be out there eventually because the numerator and denominator only differ by 2. So when we're out there at the billionth term, it's going to be the positive version of almost 1 and then the negative version of almost 1. It's just going to sit there and flip-flop back and forth. That means that our series or our sequence is not going to converge, so therefore our series is not going to converge by the divergence test out there, right? So we used a different test. We used 11.2 to actually come up with this information, even though this is obviously an alternating series. We were unable to use the alternating series test, and we had to reach back to a different test instead. So how about this guy right here? Again, we need to come up with a formula so that I can talk about b sub n so I can attempt to use the alternating series test. I can clearly see the alternating signs that scream into me alternating series. Hopefully the alternating series test will apply. So what's this thing actually look like here? N equals 1 to infinity. Well, the first thing I'm seeing is my first term is positive, so I do think it's appropriate for me to do the n plus 1 as my power right there, because when I plug in n equals 1 for my very first term, I want an even power on the -1, so that it's actually +1, so that I get a positive first term. What are our terms actually here? Well, it looks like all the numerators are just straight up 4. All the denominators grow linearly by 1, but they start at 7. So I'm thinking that this should be like n plus 6, because when I plug in 1, I want to get 7, 2, I want to get 8, 3, I want to get 9. So 4 over n plus 6. So again, I've identified what my b sub n, my magnitude of each of the terms is going to be. In this case right here, I can say we want to show that, let me back up here, we want to show b sub n plus 1 is less than or equal to b sub n. We want to show that it's a decreasing sequence right there of magnitudes. I can do that by, let's see what we got here. We've got 4 over n plus 1 plus 6 is less than or equal to 4 over n plus 6. And I think I can just give that the check mark right there. If you're dividing by the denominator is always going to be 1 larger for the next term than before. And so we're always going to have a slightly smaller term than we had the time before, right? So hopefully that direct comparison right there we're good with. The second thing we want to show is what's up with the limit as n goes to infinity of b sub n. That one's also going to be pretty easy. I got to quit forgetting my limits here. It's driving me nuts. And here, real easy limit. That's obviously going to 0 right there. We're getting an infinitely large denominator and a constant in the numerator. So based on both of these things being confirmed, so therefore, by the AST, the sequence, or the series, converges. Right? We met the 2 requirements. The limit of b sub n went to 0. We were able to show that the terms decrease from one term to the next right there with a very easy inequality. We're always just looking to show this. You just need to do algebra till it's obvious that your statement is true. Remember, back up here, I can't just write this one and say, and it's obviously true. This really just isn't clear to me that this inequality holds. We did work until it was obvious that this inequality or an equivalent version of it holds. Over here, there just really wasn't any work to do that. 4 over n plus 7 is always less than 4 over n plus 6 as long as n is positive. That's given right there. Cool. Let's do one more example and call it a day here. Last one. The sum of sine of n pi over 2 over n factorial. So immediately what I'm going to say to myself is, it's not clear to me at all that this has anything to do with alternating anything. I don't know what's going on here. I'm going to say not clear that this is an alternating series. I don't see my -1 to the n term that I'm looking for, right? So let's go ahead and write out some terms. So if n is 1, I'm looking at the sine of pi halves. Sine of pi halves is 1. And here's a helpful tip for you right here. If you ever see anything in factorials or exponentials or whatever, don't actually evaluate those. It's way more helpful to see patterns if you just leave this in the factorial form. So I'm going to do the like sort of dumb thing and write 1 over 1 factorial. Hopefully it's obvious to all of us that that is just the number 1, but that's not helpful to me. I want to be able to see like what these look like relative to each other. Now I'm going to go and plug in n equals 2. N equals 2 says to me that this is just the sine of pi. Well, the sine of pi is 0. We get no height when we've done pi radians. So I'm going to get 0 over 2 factorial. 3, we're now doing 3 pi, 3 pi halves. So that's going to put me down at negative 1 over 3 factorial. 4, we're now back around. When we plug in 4 up here, it's 2 pi again inside of sine. So we're back to getting the 0. When we get to 5, we're back to being here for sine. Sine of 5 pi halves is vertical, so that gives us 1 up in the numerator over 5 factorial, right? And so we can see what's happening. Now notice I'm referencing this as a sub n. The sequence that's associated with this series is just the terms. Now we can see that our sum of sine of n pi over 2 over n factorial is really, what are we getting here? 1 over 1 factorial. This term's just 0, so I'm going to skip it. Minus 1 over 3 factorial plus 1 over 5 factorial. And I can imagine where we're going here. So, this is good. The reason I've written out these terms is that, one, I'm now convinced that this is an alternating series. I promised you that all alternating series can be written as a negative 1 to the n times b sub n. I want that in that form because otherwise I can't use the alternating series test. I need it in a negative 1 to the n times the magnitude b sub n so that I could use b sub n to judge the convergence or divergence using the alternating series test. In its current form, I cannot use the alternating series test because I don't know what b sub n is. Now that I've written it in this form, maybe I can actually get a handle on that. And it looks like what this is going to be is the sum. I can see we're alternating with the first one being positive, so it looks like this is negative 1 to the n plus 1. What are each of the terms in here? Well, it looks like all of them have a numerator of 1, and all of them have a denominator of the odds. How do I get the odds? Well, all even numbers can be written as 2 times n, right? Because an even number is divisible by 2. Therefore, all odd numbers can be written as 2 times n plus 1, or 2 times n minus 1, or some one number difference, or some odd number of numbers different from an even number, which would be the 2n right there. I'm noticing here that if I did something like 2n, so if I just had 2n in the denominator, then I should have as my denominators like 2, 4, 6, 8, 10. All of our denominators are 1 fewer than that. So I'm thinking this is going to be 2n minus 1 factorial down here. All right. So the good news is I have now rewritten my series to be an equal series, but one that is written in the form negative 1 to the n, or to the n plus 1, that part really doesn't matter, times a b sub n term right here. We're in great shape now. Now that I've written this in the desired format, I can now attempt to use the alternating series test. For part 1, we want to show that this guy is decreasing. We want to show b sub n plus 1 is less than or equal to b sub n. So b sub n plus 1 to me here is 1 over 2 times n plus 1 minus 1 factorial. We want to show that this is less than or equal to 1 over 2 times n minus 1 factorial. Right? I'm just going to do one more line of algebra right here. If I distribute on this left side right here, what I'm seeing is 2n. That would be a 2n plus 2. 2 minus 1 is going to be 1. Since the denominator of this is always larger than the denominator of this, I think that I'm good to go right there. I think that that is my good justification. The denominator on the left is guaranteed larger than the denominator on the right. Therefore, this less than inequality certainly holds right there. So I don't think it's enough right there to state it. I think I would like to see one line of algebra to be very confident that I'm correct in that statement right there. The second thing we want to show is we want to show that the limit as n goes to infinity of b sub n equals 0. That's my limit as n goes to infinity of 1 over 2n minus 1 factorial. I'm trying to think here. I guess we really don't have any like limit laws for factorials. What we should just remember about factorials is that they grow even faster than exponentials. So this is like even more than like 1 over e to the x or something down there. This is definitely going to a 1 over infinity scenario equal to 0. So what it looks like is the case is that we can now claim that by the AST, by the alternating series test, sine of n pi over 2 over n factorial. Oh, yeah, right? N factorial? Isn't that all that was? Just, yeah, n factorial converges. All right. So we did see some crafty techniques here today. I think that straight up the theorems and the tests are easy. The hard part on your end is coming up with comparison series. Which series should you use to make a comparison against? The other hard thing on your part is you need to be able to prove the requirements associated with these tests. Proving that a sequence is going to decrease is not a trivial thing to do. Proving that a limit is equal to 0, or in our convergence, in our divergence test, proving that it's equal to a number, not always a trivial thing to do right there. And we need to be able to show a little bit of work to not suggest that those things are true, but to prove that those things are true. All right. So I can't emphasize this enough. If you short me on your proofs, and if your proofs don't represent proof, then they're wrong. So when I say to you on homework assignments and on your final exam, prove that this sequence or series either converges or diverges, if you do not prove each of the components of the test associated with it, then you're wrong. I'll back up here with the comparison test. If you do not prove that the sequence or the series you're comparing against is convergent or divergent like you think it is, and much, much, much simpler statements right there, then you did it wrong. We want to prove beyond any shadow of a doubt that we are correct, not just make suggestions. So these arguments that we're making along the way need to be tight, right? We can't just say, and this converges. There's never going to be a situation in which that's an acceptable statement to make right here. We are looking for proof, and I mean that when I say proof right there. All right. So this wraps up our alternating series and our comparison tests right here. What we're going to get next class period is the root and ratio tests. 2 more tests for convergence that'll handle roots and will handle ratios of 2 different series. In the 7th section, we'll just see more of a general strategy for like, in what order should you walk through your tests if you're trying to prove something? Because at this point, we have like already like 8 tests, or we will by next video right here. So we want to strategize a little bit, and then we'll be fully competent, at least as much as possible, in our ability to state the convergence or divergence of any sequence or series, which is excellent here. Again, our conclusion to this class next week is going to be talking about approximating functions with power series, which is a wildly useful thing to be able to do. We are going to end the class by talking about Taylor series. Taylor series are estimates at any location. A Maclaurin series is a special case of Taylor series that is always centered at 0. So those are really kind of the same thing right there. Maclaurin is just a special case of Taylor. And these Taylor series here are like one of the most useful inventions or discoveries that's basically ever happened. These are used like crazy all over the place. It really matters that we have an idea for what a Taylor series is. And as I said, you will get sort of like a sort of like a mini project in lieu of a homework assignment associated with that guy right there to fully explore the power of Taylor series and see some very cool conclusions that we can draw that we probably couldn't do if we didn't have them out there. So that wraps it up for me here today. We've got our comparison test and our alternating series and alternating series test. I will see you guys in the next video for absolute convergence and the ratio and root tests and a little bit of strategizing here. Have a good one, everybody. We'll see you next video.